about the MV1000. I'm going to start with that. So let's start from the really basic. We have a tip. Our tip looks something like this. Right, this is the cantilever, and then we have it bent, and this is the end of the tip. The end of the tip in a regular AFM is like 20 nanometers at the end. We have different tips, but we're talking about the AFM tip, the most simple one. At the bottom, we have our sample.
Yeah.
Okay. Now, we want the tip to be in contact with the sample, but how do we know that's in contact with the sample? We have to have a certain feedback, something which is going on that we can know that the tip was in contact with the sample. So in the MV1000, we have what's called the beam bounce. Okay, so we have a laser which comes out, it hits the cantilever, and then it bounces off onto a detector. This detector, okay, we call a PSD, the photosensitive diode. So the laser hits this detector, and then when the tip is in contact with the surface, so mechanically the tip, something happens to it. So we have two modes. We have in the MV1000, we have contact mode and we have intermittent mode. So let's start with the contact mode. The contact mode is the more simple, and that is when this tip is in contact with the surface. That means there's an interaction between the surface and the tip. The tip starts to bend. Okay, so now when there's an interaction, the tip will bend. Okay, we'll have a certain deformation. Let's say we'll go a little bit down. And then the laser will hit a different area on the PSD. So what we're doing is we're monitoring always where the laser is hitting this detector, and that's how we know what's going on with the tip. So for example, the tip is in contact with something high, so it will deflect like this, and the laser will hit somewhere area. If it's somewhere lower, so the deflection will be, let's say, a little bit lower.
Yeah.
So this is our feedback, our way to know what's going on the tip. So that's the contact mode, that's the most basic mode. We have another mode, it's called the intermittent mode. Okay, and in that mode, we also have everything is the same, but the tip doesn't really come into full contact with the sample. There is an interaction between the sample and the tip, but the tip, what we do is we oscillate it. So now the tip is being oscillating at a certain frequency. We're going to call this frequency omega fs, omega 0, sorry.
So this is in Z direction or XY direction oscillations?
Okay, very good. The oscillation is in the Z direction. That means it's going up and down this direction. We do have, it does also, when we oscillate it, we also have oscillations in different area, in different directions, but we're concentrating, what we're going to monitor here is oscillation up and down. That's what we're going to look for. We could also, the monitor, it's possible also to look at deflections in the horizontal direction. But in the simple mode, we're going to concentrate on the vertical direction. So we cause this tip to oscillate at a certain frequency, which is the resonance frequency. We're going to call it omega. And when the tip gets close to the sample, there's an interaction between the tip and the sample, and this will cause a certain external force on the oscillation, and the oscillation will change. Something in the oscillation will change. And that's what we're going to see in the monitor. Okay, now what kind of changes we're going to look for? We're looking for mainly two kind of changes, our phase difference or an amplitude difference. So when the tip is far away from the sample, there's no interaction between the tip and the sample, and we generate a oscillating force on the tip. In this case, we have a piezo, a PZT, which we generate an AC voltage onto. This AC voltage it is on the PZT, and therefore the PZT is vibrating. And this vibration, you know what a PZT is?
Piezo.
A piezo, yeah.
Yeah.
Okay, a piezo.
Yeah, the first what intermittent vibration,
Okay.
they are because of it is connected to piezo.
Right.
So you are supplying AC to piezo.
Right.
Piezo is oscillating, so cantilever is oscillating.
Exactly.
Now detection also, there is another piezo which is detecting the oscillation, or same piezo output is
No. Okay. So you're going into the tuning fork already. We're talking about the MV1000. Our detection is always with the PSD. This is our detector.
Mhm.
The piezo doesn't work as a detector. The piezo is only an initiator. Well, it's only the one which is, there's a PZT here, a piezo. And it's vibrating, and it's causing the tip to vibrate.
Mhm.
When the tip vibrates,
Okay.
the laser, which is hitting it, is also changing. AC change always up and down on the detector. So the detector is what's monitoring the oscillation of the tip.
Okay, so this detector output is AC output.
Yes, it could be also DC for the contact mode,
Yeah.
because in the contact mode, the motion is fairly slow.
Yeah.
The change is fairly slow. Or it can be AC mode, because mostly when we oscillate, this frequency is a couple of tens of kilohertz. Okay, so we're monitoring AC signal at a couple tens of kilohertz. Okay, but then what do we do with this signal? Okay, this is sent into a lock-in. The lock-in amplifier locks on to this frequency and can detect, or let's say filter out all other frequencies, and then all other noises are filtered out, and we're detecting only a signal from this frequency. And this way we can know if there's changes in this frequency. Okay, so let's now concentrate a little bit on the lock-in, how the lock-in works. So we have the PSD, the detector is inputting into our system an AC signal. Let's call this signal V is the amplitude signal, sine omega 0, this is the resonance frequency, plus there's a certain arbitrary phase, which is the phase of the signal.
Mhm.
Okay, so this is what's coming into our system. There is a preamplification, first of all, inside the head. This is what we call the head. Okay, this is the MV1000. You saw it, Robert?
Yeah.
Okay, so the laser comes out from here, hits the tip, and goes onto the PSD right here. Inside here we have a preamplification. So there's a first initiative amplification, and then this signal is sent out into the lock-in. So this signal, which is sent out into our lock-in, this is what we're going to call it. Okay. So how does a simple lock-in work? Then we'll go into how our lock-in works. A simple lock-in works is we have an input signal, and we have a first preamplification. Most lock-ins have a first preamp. Then this input signal is mixed with a reference signal. Right. Okay. Then this signal which comes out of the mixing goes through a low pass filter. And then we have our output. Now the output is going to be a DC value. It's not going to be an AC. So we have the input, we have an AC value coming into the system. It's being mixed with a reference signal and goes through a low pass filter, and then we have an output, we have a DC, so we have a number. And this number is a value which we can always check, is this number changing? When this number changes, so we know if something changed in the oscillation. Okay, so we'll do very simple math, just what happens in the lock-in. So let's call the reference signal, we're going to call it very similar to this one, VR, the same frequency. This is very important. Lock-in amplifiers, we have to know what's the frequency of the input signal. So the reference signal must have the same frequency as the input signal. Okay? So the same frequency.
But the input frequency is variable according to the sample characteristics, right?
Right. It will change a little bit. You're right, but we know more or less the frequency. So but we're going to only look at one frequency. We're not going to look at other frequencies. It's true. When the tip is going to be in contact with the sample, there's going to be external forces which are going to change and give extra frequencies. But we're looking only at one very particular frequency, the resonance frequency. We're only looking at that one. We're not looking at other frequencies. There is, maybe you heard of PLL, where there we do look at different frequencies. We look how the frequency is shifting. In our case, we're not looking how the frequency is shifting. We're concentrating only at the resonance frequency. And this is the most important thing, is the reference also has a certain phase. So the mixing mathematically is the product of two, this times this. Okay, so if we do the product of these both, we will get V S times V R sine T plus phi signal times sine plus phi reference. Okay, this is this times that. Didn't do anything special here. Now, what does this equal? We can do a little bit, some very simple trigonometry. Trigonometry, thank you. And sine times sine is at the end, this is equal. So at the end of the day, this thing is equal to half V R V S cosine phi signal minus phi R minus cosine of 2 times the frequency plus the phases. Okay, this is what we get at the end. If we just this is what happens after the mixing. So the product is equal to this.
So if the noise frequency is equal to the reference frequency, then it will also get at output of our lock-in?
That's true. If the noise is exactly at the frequency of the input frequency, that noise will also, we will also have the noise in the signal. But most of the noise is what's called white noise. So it's at all different kind of frequencies, and it's not always at the same frequency. So it could be at one time we're going to get a little bit noise, but over the entire scan, we're not going to always have a constant noise. It could be that here and there some noise will come in. Now if we look at this part, we have here this side, the first or whatever it's called, argument is DC. There's nothing here which is oscillating. Okay, this is AC with twice the frequency. So if we take this thing and we put it through a low pass filter, that means we filter out high frequencies, then we will only be kept with a DC number.
Yeah.
So mathematically what we're doing is putting through a low pass filter is integrating. And it's important, I'm saying, I'm not just doing totally theoretically, because in the program, the software, we're going to use what I said. For example, this integration time can be, in the software, you can choose what's the integration time. And we're going to see soon why it's important to choose the integration time. So,
is it integral gain, what we are choosing there in software?
No. The gain, that's a different story.
Oh.
So going through a low pass filter is really integrating this entire term by time. Now, if we integrate a cosine function, which is, it's a cycle, it's a periodic cycle. It's always going, has a certain cycle. So if we integrate over a time which is more than one cycle, then we will get 0. Because at the average it's 0. Okay, we have here, it's only cosine, it's going up and down. Oh, this is the 0. So if we integrate over a longer period than the cycle, then we will get 0. That means that tau, the integration time, has to be bigger than this value. Okay, so for example, this value, this is the frequency. Okay, no, that's 1 over the frequency. Sorry. Okay, so let's say if our frequency is 1 kilohertz. That means that tau has to be bigger than 1 millisecond.
Okay.
But if this is, let's say, 10 kilohertz, then tau, this has to be bigger than 0.1 milliseconds. Okay, so at the end of the day, after we integrate, we're left with the DC value. What's the time? Whenever you have to go, so let's go. Okay, so we're left with this value, only the DC value, cosine C signal minus phi r. Okay. Now just to make it simple, we'll call this part V, and this we're going to call theta, just to make it simple. But we see that this part has to do with the amplitude of the signal. That means if the signal, if the tip is going to have an input signal which the amplitude is going to change, remember we have the PSD. So we have the laser which is hitting the PSD. And it's oscillating on the detector at a certain amplitude, also at a certain phase. But when the tip is going to get close to the sample, there's going to be a certain force between the tip and the sample. In general, that force will make the oscillation smaller, the amplitude of the oscillation smaller. So we're going to see here a smaller amplitude, and our V signal, the amplitude will be smaller, and therefore this whole entire
Is small.
term is going to be smaller. Now we can also monitor a change in the phase. That means when there's going to be a certain interaction between the tip and the sample, the phase, even if the amplitude won't really change, but there will be a shift in the phase. Let's say it's oscillating like this, and suddenly when there's a force, so we'll stop for a second or change a little bit, and then oscillate in a different phase. So we're going to have a certain change in the phase of the signal, and then this value will change. So most in the lock-in we're looking are at a phase change or at the amplitude change. Now, this is, as I said, a general lock-in. In our lock-in is inside the SPN controller. That's where the lock-in is. We have two reference signals. Until now we talked about one reference signal.
Mm-hmm.
In our lock-in we have two reference signals. They both have the same frequency, but there's a change in their phase between reference 1 and reference 2. That's why I'm going to keep this one. So the second reference is the same as the first reference. It's only different by a phase of 90 degrees. Okay, so if this was the signal from the first reference,